Great. Hi, everyone. Our project is NourishNet, which is a pipeline for determining the severity of price spikes in global commodity markets. Before getting into the technical details of our project, let's take a look at the main problem we're trying to solve. Here in the US, Americans spend roughly 10% of their income on food. That means that here in the US, we live with relatively high amounts of food security. But in other communities around the world, they could spend up to as much as 90% of their income on food. That means that in these communities, they live with relatively low amounts of food security. Because of this, that means world hunger is not yet a solved problem, and millions each year suffer from starvation as they cannot afford when price spikes occur. A proven approach to tackling this problem has been the use of sending out early warnings for classifying price spikes to reduce the food security strain on these communities. By sending out these warnings to these communities, this enables them to be able to stockpile food before prices inflate such that they have stock when they otherwise would not have. To understand what these early warnings look like, you need to take a look at the Food and Agriculture Organization, or otherwise known as the FAO for short. The FAO has developed the GIEWS system for sending out these early warnings for price spikes in food commodities. A component of the system is this map, where individual nations and their commodity markets either have no warning, a moderate warning, or a high warning associated with them. This is currently determined using purely a statistical method, and we hope to augment this method with the use of deep learning. To do this, we would propose our NourishNet pipeline, which through multimodal data processing, price and warning prediction, and interpretable insights will provide communities additional levels of food security. Before diving into our AI solution, no machine learning project is complete without the data that powers it all. The goal of our data sourcing is to paint a good picture of the market activity that's occurring today. To do this, there's already a variety of organizations dedicated to collecting data in the space, but that also means there's a lot of data for us to go through and figure out what paints the best picture for our project. To do this, we developed a multimodal pipeline to easily test out new data sources and see how they affect our output. Along with this, we talked with industry experts on what features they best recommend to paint this market picture, and ultimately, we had to balance the richness of our predictors with the data overlap scarcity, as pulling 50 features may paint a great picture, but it may only be available for a year or two for all countries we hope to analyze. By putting these data sources together, we get a graph that looks like this, which is absolutely horrible to try and interpret. But with some further analysis, we were able to narrow down these sources to these final data sources. A majority of these sources come from the FAO, with the Proteus Index being the main indicator for food security by nation. Beyond this, we also get a good look at food price by pulling the FAO and World Food Program indices and commodity price data. Commodity futures help us determine the confidence of the market, and data on harvest states the yield for that season for given food commodities. And finally, article sentiment on both food security and agriculture reports allows us to encode market outlook into our time series data pipeline.
Now that we understand the data, let's look at the predictive capabilities of our pipeline. Starting with predicting commodity prices, we use an encoder transformer tailored for our domain, and we'll look at the architecture of that more later. For the model, we train on commodity markets rather than country markets because commodity markets are relatively similar between countries, even viewing them globally. For our results, we achieved an MAE of 0.054 trained on a more general model of all wheat commodity markets. This beat out the previous state-of-the-art of 0.072, which is trained on a specific market and specific commodity. Looking at the plot on the right, you can see as the model tries to predict more months in advance, the error increases, flatlining around 6 months. We believe this happens because long-term trends have similar predictability compared to short-term trends. It's also important to note that the model does not have any additional information that it would not have in a real world when predicting multiple months in advance. Correlating this error to USD, it's about $80 per month in a domain that's thousands of dollars. And correlating this to commodity items, in Argentina, this would be about 200 kilograms of wheat saved per month. Looking at our warning prediction model, we also use an encoder transformer with a classification output where we follow the GIEWS system. For labels, we scraped FAO warning reports from 2015 to 2024, where we achieved an average precision of 71.48% weighted across all classes. This weighted measure was used to account for the severe class imbalance issues and provides a single summary statistic of model performance across all precision recall thresholds. Now that we understand the regression and classification model, let's see how it all goes together. First, data comes from a variety of sources that we listed earlier that gets inputted into our price prediction model that is an encoder transformer with a couple of changes. First, we add a global average pooling to fit our domain's needs, dense layers are added to the feed-forward network for increased learning stability, and a dropout layer is added to reduce the likelihood of overfitting. And we use 10 transformer blocks for these price predictions. Data is inputted into the model and then outputted time series trend data. That ultimately gets inputted into the warning prediction model. That is similar to the price prediction model, but with an added dense layer for classification. The time series trend data gets inputted, and then the final warnings get outputted. Therefore, this results from an overall prediction pipeline that goes from raw data from online sources to actual warning predictions that can be used to generate future insights.
Now that we understand the predictive capabilities of our model, we now need to see how we can actually provide these technical insights to the communities that would benefit from them most and ultimately provide higher amounts of food security. We believe the best solution for this is this chatbot interface, which provides non-technical users a way to interact directly with technical information, decreasing their barrier of entry to interact with this, as well as providing easy to understand yet powerful insights for the ultimate decision makers for these communities. We showcase this through this demonstration on the right, where it offers multilingual support, as you can see on the drop-downs on the top. Another drop-down is also for selecting the specific nation that this discussion will be about. The LLM is prioritized to have friendly conversation with the user, tying specific actions to the warnings associated with that nation. So when the user asks something like, "What should I do?" correlating with a specific nation, it might also look for specific data insights to bring into it, such as already predetermined responses to frequently asked questions, articles in order to cite its sources, or even crisis videos in order to give examples of why a high warning might be happening in the first place. Let's look at how this actually works. On the left-hand side, you see the interface we were looking at before, where a user will send in its query of information. This is where we go to the top of the diagram, where we use a chain of thought framework with the same large language model, just using different contexts throughout it processing the information. First, the filter LLM determines if the question was appropriate and is relevant to what this model was fine-tuned. And then this is passed to the speak LLM, which is that friendly conversation piece I mentioned previously, where there's then the optional data provider LLM, where again, it could be a set response to a frequently asked question, some article in order to kind of cite its source, or even a crisis video to showcase warnings, so that the user itself could even do further research to back the credibility of the model. These are all combined then into a final chat response, sent back to the interface, and this cycle continues throughout the entire conversation. But once we actually develop this chatbot interface, we by no means claim to be domain experts in the space of making warning models, or even in the space of providing decision makers around the world that affect millions of people insights which will affect these communities. However, there are domain experts in this space, which brings in the United Nations FAO, who has developed that GIEWS warning system we mentioned previously. We went to them asking, how could our NourishNet pipeline aid the work that you're doing already, or how can we aid your existing warning system? And from sharing our ideas, we are now actively collaborating with the United Nations FAO to further develop our solution further, along with the GIEWS system, to provide actual communities with the insights we're getting here at MSOE, the ability to increase their food security and ultimately save lives. What this more specifically looks like is we've been communicating with their data lab, which is their growing data science team, as well as those responsible with the GIEWS system. They've currently validated our NourishNet both predictions and the insights we've provided as avenues they'd like to explore further, and this further exploration or collaboration will look like including the existing statistical analyses they've been spending years researching into this pipeline, as well as making sure the output of the chatbot is aligned with actually providing decision makers accurate and well-informed amounts of information. And that's been an overview of our NourishNet pipeline, where we take a variety of different data modalities, perform predictions on them, and then provide them in an easy to understand way so that communities can understand them, even if they don't have a technical background. And all of this would have not been possible for not the ROSIE supercomputer available here at MSOE, as our overall model is around 50 billion parameters at a large scale, providing the most accurate insights. And to balance this, since we're working with the FAO, We were also able to develop a 7 billion parameter model version, both of which I'm pretty sure would make my laptop explode. And that was to really balance its deployability as well as its accuracy. And ultimately, ROSIE is what made possible us doing big data experiments across all these modalities, all these sources, all these organizations, across decades of data collection, putting that into models to do quick iterations on those experiments and seeing how they directly affect our output, and ultimately even using state-of-the-art generative AI solutions that are coming out every single week to provide the best insights possible. Thank you.
Thank you for the presentation. Great job. It seems like one of the core capabilities of this pipeline is the ability to predict commodity price, which is amazing. If you can solve that problem well, you could probably just feed the world. So I guess I'm curious about what similarities do you see to other tools or methods that have been created to do price prediction? What can you learn from those and apply to this workflow?
Yeah, like we mentioned, a lot of the previous state-of-the-art methods in this domain specifically really focused on nation commodity pairs and those really like very low-level markets. And this one takes a more unique approach, both in the model that it uses and some of those methods, as well as looking at the commodity markets at large. But for other domains, like you mentioned, like maybe even stock prediction for just different prices, we think that this could be applied in some way. That would play in part to that multimodal data pipeline we mentioned where we're building, where you just grab them from online, set your response variable, and it would be able to generate those types of insights.
Sure, but there are billions of dollars being spent to develop those sorts of models for other areas. So that's a great opportunity, I think, to look at, well, what types of structure are they using? What types of models are they using? How well is that working? And see if that's something that could be applied in this area as well.
Yeah, some of that like prior art we were looking at, that's really where a lot of the transformer architecture comes into play, as it's really the state-of-the-art time series predictor. We have looked at some of those applications, like you mentioned, billions of dollars are spent by huge like stock management firms in order to get those type of predictions and accurately and as early as possible. And some of what's publicly available in those research papers, we brought in through that transformer architecture, like we said, adding global average pooling to match the dimensionality in general, as well as some fine-tuning.
Okay. Do you have any examples of all these components working together? And do you have any data that would show the accuracy of your prediction model?
For warnings or for cost?
Both.
Yeah. So for the cost, we do have this being applied to currently commodity food prices, like we mentioned, all those different data sources, and then directly being provided by the chatbot. For the output that we're getting now, correlating the like 0.054 just kind of normalized error to actual insights, that's around $80 worth of error, which is on a smaller scale compared to thousands of dollars in the market today, are around like 200 kilograms worth of food. And then for the warning prediction model, that 72% that we mentioned, we still think that type of accuracy is good in this space, as we're using only price in order to determine that type of security output. And we're thinking about in the future including things like the stock to use ratio or other security metrics that might paint a better picture.
Thank you.
And can you feed the results of this directly into the buying nature of these different countries?
I think that's where kind of the chatbot interface, at least where we came up with, where it's more of the decision maker's role in that space. As the FAO, when communicating with them, we asked that same question in terms of why not make it a fully automated system? And I think it really comes down to just like the accuracy of the model. And since this affects millions of lives, especially in more underdeveloped countries, you have to have kind of a point person to look at it, again, glean those insights, and then ultimately be the person to make the decision.
Yeah, I mean, something similar to this, not as noble as solving world hunger, but companies like Walmart actually does a lot of data science, believe it or not, on predicting the sales of bananas, among other things. But bananas are something that are more of an impulse buy. They need to have exactly the amount of ripe bananas per store, because certain stores sell more bananas than others, and they're perishable, right? You're not going to buy the black
Yeah.
bananas. You want the nice greenish.
The
bananas,
shelf life,
right?
yeah.
Yeah, shelf life is there. And so they use a lot of GPU accelerated data science on this platform called Rapids. And it can apply directly, the buying is all done through computers, and it all directly applies to profits.
That's
And you could apply this to world hunger on a more noble scale,
Mm-hmm.
or you could sell bananas. But in either way, it seems similar in nature.
Yeah, that's a future for this pipeline. Yeah, that's really interesting. I think that is interesting to hand that off in that type of decision making, especially as more and more people understand AI and are including it in their products.
It's great. Good? Very good. Thank you. Okay.